I want to introduce to you some more tests beyond just these simple formulations of these tests, because the Z-test that we've looked at doesn't work as well if we have very small samples. And there are other tests that we may need to employ if we have discrete distributions, if we have very small number of samples. There may be cases where instead of looking at some sample of the before and some sample of the after, we can look at exactly paired elements from the before and the after. We can resample the population and the exact entities in the population before and after. So we can look at the exact same device in the before and the after, and that can give us some additional predicative or some additional hypothetical power. Our next question is, why is everybody suddenly so testy? And I want to share with you some common statistical tests and their mechanics, and share with you how we might use these beyond just our simple Z-test in order to answer the same sorts of questions. As I said, when we're dealing with our Z-test, we're typically talking about, some normal distribution. But I want to introduce another distribution to you, the t distribution. And you can see I've plotted the normal distribution and the t distribution together, where the normal distribution has parameters, the mean and the standard deviation, the scale and the location. And you can see here this is just a location of 0 and a typical standard deviation of 1. My t distribution has one parameter, and it relates to the number of degrees of freedom. And for my t distribution, if the parameter for that t distribution is very, very large, it converges to my normal distribution. So here I have 1 billion degrees of freedom. It's basically equivalent to a normal distribution. It converges. Where this t distribution is helpful is when I have a very small sample. If I look at very few degrees of freedom, you'll see a divergence between my t distribution and my normal distribution. What we're leading up to is this. Beyond the Z-test, we have other statistical tests. You may have heard of them, like students' t-test. And where they differ is the computation of the test statistic and the distribution we're referring to. Instead of referring to a normal distribution, we're going to refer to a t distribution, which is closely related to that normal distribution, but has certain properties that allow it to be a little bit more robust in developing these p-values if we have very small sample sizes. Let me show you how the t-test works, at least mechanically. I have my population. I have some sampling of that population because I can't see the population itself. It's a relatively small sampling, just 10 elements. This is a big population. There's, I think, 100,000 or 1 million elements, and I can only look at 10. Kind of sounds like those studies that you read in the newspaper. We surveyed 50 people, and they told us something about all 300 or 400 million people living in the United States. Doesn't seem like a big enough sample size. But we might be able to, via this t-distribution, at least more robustly make certain assertions about the population given that small sample size. Here's what I'm looking for. I'm looking to see whether my population mean is at some fixed value that I'm aware of, some set value. I'm looking to see whatever this population represents, if its mean is 75, maybe that's what it was before, and I'm looking at what's happening after. Maybe I'm just trying to guess. Maybe I'm trying to say, well, I think the mean value across everybody is 75, but I can only see the sample. Let's see if we can prove that it really is 75. My null hypothesis, which I'm looking to accept or reject, is that the population mean is equal to 75, and my alternative hypothesis is, no, it's not. You can see this is two-tailed. What I'm going to do is I'm going to compute my statistic here, my test statistic. And I'm going to compute it in the same way that I've done with my Z statistic, take the mean, look at its distance from the target value, and then normalize by this standard error. Once I have that test statistic, I'm going to see what the probability of that test statistic is given my distribution. Here, since I'm talking about a Z test, I'll use a normal distribution, and everything kind of matches up with what we've seen before. This matches up almost identically to the stats model z-test, with the slight exception that the stats model z-test doesn't look at the population standard deviation because it doesn't know what it is. It doesn't take that as a parameter, but instead tries to estimate that using the standard deviation with the Bessel's correction. Well, this isn't quite a z-test because usually with the z-test, we're assuming that we know the population standard deviation. And so here we're beginning to bend our definition a little bit. It is a type of z-test, but it's not typically what people talk about when they talk about the z-test. Instead of doing this with my z-test in this formulation, let's talk about a t-test. SciPy gives me the ability to do a t-test on one sample. Let's take a look at what this code is saying. I have a sample. I think the population mean is 75. Compute my test statistic for me. Given that test statistic, compute my p-value. That p-value assumes the t-distribution, and thus, if I wanted to recapitulate exactly what SciPy is doing behind the scenes with this, all it's doing is, it is taking my test statistic, which I computed before, and it is just trying to figure out where on a t-distribution this would appear, and it's doubling it because this is two-sided. And you can see the difference between the CDF on the normal distribution and the CDF on my t-distribution. There's a slight difference here. All the t-test really is a changing of the underlying distribution against my z-test. Instead of a normal distribution, I look at this t-distribution. And all that t-distribution is something that approximates a normal distribution in the limit, but for small sample sizes has a slightly different shape with longer tail. So it takes into account, well, just because you didn't see it in 10 samples doesn't mean it's not there. The normal distribution drops off really quickly, whereas the t-statistic doesn't, or the t-distribution doesn't drop off as quickly. So it can account for, just because you didn't see it in a small scale doesn't mean it didn't happen, and account for that better. This is how we can tie out our SciPy t-statistic against the actual mechanics, and you can begin to see every one of these tests, compute the sample statistic, try and figure out what's the probability that's in that rejection region, that's your p-value, and then make a judgment. For a p-value of 0.59, I don't think I can say one way or the other. I don't think I can say to reject the null hypothesis, so I'll let it stand for now. I'll let the null hypothesis stand, and so from the data that I see, it indicates that the population mean may be close to 75. Now, let's go a little bit deeper into our tests. In addition to this t-test, I have tests that I can perform on discrete distributions. Let me show you another distribution. Here, this is the chi-squared distribution, and it is parameterized also on my degrees of freedom. Here, you can see it plotted for different values of k, which are these degrees of freedom. SciPy calls it df for different values here. So here you can see what our distribution is. In our chi-squared test, we change the distribution and we change the test statistic. Our goal is to be able to answer questions like, is a die a fair die or not? Is something that has discrete values, not continuous values, matching to a particular distribution that we expect given some sampling? And so let's actually try to do this with some rolling of a die. Here, I have randomly generated some data. 50 elements, relatively small number. And I've generated them from a uniform distribution from 1 to 7, here using random.choice. This is a fair die. Each one of these values has an equal probability. And if I were to plot the histogram of this, I should see that roughly equal. You can see if I look at the values and the counts, each one of these has approximately the same count. I don't have a big enough sample for these to start to really converge on something that is properly uniform, but you can see they're beginning to get kind of close, and if I were to raise the total number of these, you can imagine that this starts to become closer and closer to representing that this is uniformly chosen. Here's what I'm looking to prove. My null hypothesis is that every one of these possible values has the same weighting. It is just as likely that I got a 1 on my die roll as I got a 2 or a 3 or a 4 or a 5. That's what I'm trying to show with my null hypothesis. And with my alternative hypothesis, I'm trying to show the opposite. I'm trying to show, looks like you're cheating. It seems like you keep getting 7s at the craps table. This is what I'm trying to show with my alternative hypothesis by rejecting my null hypothesis. How do I do this? Well, I can compute my chi-square test. And SciPy gives me the ability to do that. I give it the counts that I see, and I compute my test statistic. I get a p-value from that test statistic. It's pretty much the same as before. And I can, from that p-value, determine p-value of 0.83. So this means that there's an 83% probability that I saw this test statistic given the null hypothesis. That's a pretty high probability that the null hypothesis it can be accepted. I can't reject the null hypothesis with this. If I want to see how to actually formulate this, let's take a look. What I'm going to do in my test statistic is I'm going to take the actual counts that I see, and I'm going to see how far away they are from what the expected count I would think there would be if they were even. So I take the look of the size of my data. I look at how many values that I've computed, like there's 6 values, and I did 50 rolls. So I should see 50 divided by 6 in each bucket. I take that and I square it, so I'm looking at the squared distance from my mean count or my even count, and then I normalize this by the size of my data set and the total number of values that I have. I look at the sum of that, and that's my test statistic. And if we try to tie out my SciPy test statistic against my test statistic here, you can see they tie out exactly. This is just how this is computed. For my chi-squared test, all I'm doing is taking that test statistic and I'm seeing where it lies on a distribution. A normal distribution? No. A t-distribution? No. A chi-squared distribution. All of these tests have those two parts, test statistic and the distribution against. You can see I've tied this out. And so I can compute this by hand. I can compute this with SciPy. Whichever the case may be, I probably want to do it with SciPy. It's a lot easier. It's important that I understand what the underlying assumptions are, how I formulate this question, how I formulate my null hypothesis, and how I interpret these results. That's what's important. Now, let us take a look at something in scipy.stats. If we look at the t-test in scipy.stats, we have a couple of t-tests, an independent one, a relevant one, a one-sample one. What do they all mean, and what's the difference? Well, it turns out that we can do t-tests in a number of different ways. We can do what's called a paired t-test, which is the case whereby I have 2 samples of the population, but I'm sampling the same entities. I'm not looking at a random sampling of all the devices before something happened and a random sampling after something happened. So there could be different devices. I'm looking at the same devices before and the same devices after, but I am still looking at a random sampling. I'm still looking at a subset of the total population. And so here I have my total population. I'm going to assume that they are the same size. My before sample and my after sample, here, this is if they are independent of each other. So here, this is assuming that I have some sampling from before, some sampling after, they don't line up. Or my paired sample, I'm assuming that I figure out these are the devices I'm going to look at. It's a subset of the data set, only 25 elements, but I'm looking at the same before and after, and that gives me a little bit of additional power. If I compute my independent t-test, what I'm saying is the before sample and the after sample were independently chosen, which is the case. They were independently chosen. I chose both of these without replacement, without looking at each other. If I want to say that instead of looking at them independently of each other, I'm looking at them relative to each other, I'm looking at the same sampled elements, what I can do is I can compute the pooled standard deviation for, or rather, if I wanted to tie this out, if I wanted to tie out how this independent t-tests work, what I could think is this is basically just computed by looking at the pooled standard deviation of the before and the after sample, computing the test statistic from that, what's the difference in these means. Here you can see my test statistics should tie out exactly, and then figuring out where this lies in my t-distribution. But if I'm looking at paired samples, I do things a little bit differently. What I do is I use t-test relative. And I get a different statistic and a different p-value. And boy, do I get a different test statistic, and boy, do I get a different p-value. It is almost certain that I will reject this null hypothesis because there's very little likelihood that my hypothesis that nothing happened, that these represent the same thing, that there was no difference here, is very low likelihood if I'm looking at the same element before and after. And I get some additional power in this. Well, how do I compute this paired t-statistic? It's not altogether too different from before. What I'm going to do is I'm going to look at the difference of the means, and I get that. And I'm going to compute my statistic by taking the difference of the means divided by the standard deviation of that difference divided by or normalized by the paired sample size. So here you can see I've tied out my test statistic. And then I'm just going to see where that test statistic lies on my t-distribution. But my degrees of freedom will be different. Previously, my degrees of freedom needed to account for just the sample size that I'm looking at and how many elements. But when I'm looking at two pieces of data, I need to account for the degrees of freedom in one of them, the degrees of freedom in the other, and the sum of those degrees of freedom. If it's the case that I want to look at this paired sampling, I can look at it a little bit differently. I can go back to my original one sample t-test, and I can see that my paired sampling t-test is really just the same thing as a one sample t-test, where I'm assuming that the population mean is 0, where I'm looking at the differences in these, and I'm just assuming the population is 0. And so there is a close relationship between these three different types of t-tests, but it is important for you to understand when you're doing this t-test on two samples, are they independently selected, or is it the same sample, and what does that mean for the computation of this statistic? Now, before we continue, why don't we take a very short commercial break?